All right, so how do we get to making a prediction or a forecast? We have to provide two things: the estimated property price and the range that goes with the price. Because this is what the pros do, and we'll also provide an estimate of what the home is worth plus a degree of uncertainty around that number. The estimated price is easy enough, right? Because once we have the theta parameters for the model, all we have to do is plug them in, and then together with the values for the individual features, we get an estimate. We get our y hat. But what about the range? Where does that come from? The range will actually depend on the shape of the distribution that you're working with. If we know the distribution, we can estimate the range very accurately. And here's the thing. Our go-to distribution is usually the normal distribution. Because the very, very nice thing about the normal distribution is that we know its shape. We know that for a normal distribution, 68% of the observations are between these 2 points. 68% of all the values in this distribution are within this purple range right here. And for a normal distribution, we also know that around 95% of the values are between these 2 points here. 95% of the observations fall within this pink range that I've highlighted right here. The individual points that I've drawn on this histogram right here actually have a name. They quantify the amount of variation around the mean. The mean is right here in the middle of the distribution. And the distance from the mean to that right purple point is called 1 standard deviation. For a normal distribution, you'll usually see the Greek letter sigma used to denote the standard deviation. Now, what about the other points that I had drawn on here earlier? Well, the left purple point is at minus 1 standard deviation. Minus 1 standard deviation from the mean. And for a normal distribution, as we said before, around 68% of all the observations lie between minus and plus 1 standard deviation. Okay, what about the pink points? Well, the right pink point is at 2 standard deviations, and the left pink point is at minus 2 standard deviations. And as we've said before, approximately 95% of observations lie between plus 2 and minus 2 standard deviations for a normal distribution. Now, let me ask you this. If this green point here, right in the middle, is our estimate for the property price from our model, our y hat, what is the distribution that we're going to be looking at here? Any guess? What's the distribution that tells us something about the variance in our price estimates? Well, we're going to be coming full circle here. It's actually the distribution of the residuals from our regression. This is the reason why we cared so much about whether the distribution is a normal distribution or not. Now, the next question you might ask at this point is, well, okay, so if the distribution is the distribution of the residuals, then what do the purple and pink dots represent? How do we get our range? Do you remember our mean squared error? No, the mean squared error is not the purple dot, but we can make one small modification to the mean squared error and get something very, very handy for calculating the range and making predictions. And that small modification is by taking the square root of this thing. By taking the square root of the mean squared error, we get another metric. And this one is called, surprise, surprise, the root mean squared error, or RMSE. And it's this metric, the RMSE, that has a really, really nice interpretation, because the root mean squared error represents 1 standard deviation of the differences between our actual and our predicted values. The root mean squared error is 1 standard deviation in the distribution of our residuals. So let's look at the chart again. to create our range around our estimated price, our so-called prediction interval, the first thing we choose is how wide we want that interval to be. Say we want to cover around 95% of the observations. Then we would use 2 standard deviations either side. And this means taking our prediction and adding 2 times the root mean squared error to it for the upper bound and subtracting 2 times the root mean squared error for our lower bound on our prediction. And that's how we get the range. In our Jupyter Notebook, this means simply taking the square root of our mean squared error that we've already calculated. Coming to the cell where we've got our data frame with our mean squared error, what I'm going to do is add another column. So I'll put a comma here, go to the next line, single quotes, and put RMSE here, and then a colon. And now I can take this entire list here, copy it, and then here, what I'm going to do is I'm going to use numpy and call the square root function from numpy. And as an argument, I'm going to pass in the list that I just copied. And what this will do is I'll take the square root of all the items in the list. Let me refresh the cell. Here we go. Now that we've done that, I want to give you a challenge. Suppose we have an estimate from our model, for a house price of $30,000. Can you calculate the upper and lower bound for a 95% prediction interval using the reduced log model? In other words, can you calculate the upper and the lower bound for the range around this estimate? I'll give you a few seconds to pause the video before I show you the solution. All right, let's take it from the top. So I'm going to add a print statement, and I'm going to spell it out. So I'm going to say 1 standard deviation in log prices, because we've got units, is, and that will be the square root of our log mean squared error. So np dot square root reduced underscore log MSE. Agreed? What's that equal to? It's equal to this much. Now, what about 2 standard deviations? I can calculate that simply by taking the first print statement, copying it, and then multiplying this whole thing by 2. Here we go. This is 2 standard deviations. The upper bound for the prediction interval will be equal to our y hat plus 2 times the root mean squared error. Now, I've been pretty sneaky and I've given you the y hat in dollar values. So you actually have to use a log transformation, np.log 30, since our model is given in thousands, and then you have to add 2 times np.square root reduced underscore log underscore MSE. So this is our y hat plus 2 times the root mean squared error. Let me print that out. So I'm going to say print the upper bound for a 95% prediction interval is, comma, upper underscore bound. That's equal to 3.78 approximately. Now, if we wanted to see this in dollar values, then we can say, well, the upper bound in log prices for a 95% prediction interval is this much. And I can copy this, paste it in, and I can say the upper bound in normal prices is np.e to the power of upper bound. So let's see what that is. I can make that more explicit by multiplying this whole thing times 1,000, putting a little dollar sign here, and there I've got my upper bound. The lower bound is very, very similar. I can even copy these 3 lines, paste them in, and change this to lower bound is equal to np.log 30 minus 2 times the root mean squared error. Then I can change my print statements to read the lower bound in log prices for a 95% prediction interval is lower underscore bound, and the lower bound in normal prices is np.e times lower underscore bound times 1000. Let's see what this reads. The lower bound in this case is $20,635. Now, the trick with this challenge is to do the addition of the root mean squared error and the transformation in the right order, because otherwise you'll get a very, very different result. The incorrect way of calculating the upper bound would have been to take 2 times the root mean squared error and simply say, well, okay, we've got an estimate of 30,000, and then we're going to add to it the transformed value np.e times, and then the root mean squared error times 1000. So this was the little trick in how I phrased this challenge. In summary, we often look towards the root mean squared error when we're interested in the predictive power of our models. And to some extent, we can use the root mean squared error to also compare the models. And the reason is that the root mean squared error is a very good measure of how accurately the model predicts the target, because we can determine a range. The width of this range is a very important criterion if the main purpose of the model is prediction. And this is a big contrast to something like R squared, because R squared says absolutely nothing about the predictive power of the model or the prediction error. Okay, so we're slowly coming towards the end of this section. In the next lesson, we're gonna finish it up by building a valuation tool for our boss in our real estate office. And that's gonna involve probably updating the prices to reflect today's dollar values a little bit. I think the Boston upper price of $50,000 is not really that accurate anymore. And we're also going to be looking at how we can create a Python function with optional arguments. So arguments where there's already default values set, similar to what we've seen with Seaborn and Matplotlib. And we're going to cover the syntax, the Python syntax, how we can create functions like this ourselves. I'll see you in the next lessons. Take care.